Greetings everyone. We are again back with a new session in the Developer Talk series. I hope you had lots of fun in the last session by Ben. It was really an interesting one. Now we have Mr. Sarfaraz to host a session on demystifying big data, the new uprising technology of the day. So, a bit about him. He's a big data enthusiast, currently working as a software engineer 3 at Walmart Global Tech India, actively working in the field of data engineering and application engineering. He has a vast, uh, vast tech stack under him: Apache Spark, Scala, SQL, Java, Snowflake, Apache SQOOP, Apache Hive. It's a pleasure to have you, sir, over at Equinox, and over to you.
Thank you so much. Introducing me. Yeah. So I feel honored to be part of IIIT Lucknow's event, hackathon event. So yeah, so we can start with the talk then. Okay. So welcome everyone. So whoever is listening to the session right now. So the session would be understanding big data, I would say, and we will see various aspects of big data, and at the end we will talk about how you can land up your career into big data as a data engineer. Okay, so I assume that you all are like BTech or MTech guys who will be passing out within 1 or 2 years and looking out for a job. So yeah, from that point of view, we will be talking about your aspiration and how can you land into a job. So yes, so we can start with the session. Yeah, this would be our agenda. So I'll be introducing you to big data, then challenges that we face in our day-to-day life, as an engineer with big data. Traditional approach, what we used to do to process the data earlier. Then we'll be introducing you to distributed computing and a framework called as Hadoop. Then we will look into the Hadoop ecosystem, and we will finally, yes, as I said, we will be talking about how to build a career in big data. Okay, so let's start with the agenda. Yeah, introduction to big data. So what is actually big data? Okay, so big data is a collection of, say, humongous data sets. Okay, multiple data sets which forms a huge collections of data. And when I mean huge collection, I typically mean that data is not in GBs and we don't talk in MBs. Okay, so data has to be in terabytes and petabytes. So this is the volume of data which we deal with, okay, for in any big data computation. So this data includes kind of some properties. Typically, these properties are known as 3 V's. So the 3 V's includes volume, velocity, and variety. Okay, so to at least qualify as big data, let's say I have some data, so I want to identify that, okay, whether I am able to call this data as big data or not. Okay, so any data can't be a big data. Okay, so to qualify their data to be called as a big data, at least you need to fulfill two of the properties out of the 3. Okay, either volume or velocity, or velocity or variety. Okay, or volume and variety. Okay, so what does we mean by volume? Volume is, as I said, that it needs to be humongous, size of data in petabytes and terabytes. Okay, and velocity, and that means the rate at which the data has been produced should be very high. It doesn't mean that you have data which is generating every yearly, it is increasing every yearly. No, that shouldn't be case with the big data. Means when I mean velocity, let's say Facebook in 1 minute generates approximately 4 to 5 million likes. So you can think about the data generated by this kind of social platforms, that how much data is being generated and how it is difficult to handle and store this data, right? And that comes variety. Means the data should be in variety of forms. Let's say there can be structured data, there can be semi-structured data, and there can be unstructured data. Okay, when I mean structured data, that means you're typically your RDBMS data, that is tables in the form of rows and columns. Those are properly structured that have a particular defined schema, right? So semi-structured data are your JSON data and your XML data, which are kind of structured, but they do not have a proper schema, right? Then we have the unstructured data, which doesn't have any structure or nor it has any schema. Those are text files, your media log files, your PDF. Okay, these falls under unstructured data. So these are the type of variety of data that we do have. So this all can come under big data. Next, let's look into the sources which are generating big data or which are contributing towards big data. So social media, as I said, like Facebook, Instagram, there are many other more like LinkedIn. All all used to generate millions and millions of data every minute. Okay, every status you put, every photo you upload, that's all contribute towards big data. Banks, yes, all the transactions that has been done you can think about that the world is doing how many transactions in even not in minute, even in second. You can think about the data that has been contributed. Then CCTV cameras, which are continuously recording over where it is installed, like 24/7 it is installing, and it is being stored into some location, maybe in the cloud or maybe say in your internal servers. So that's contributing toward big data. Then all other websites, okay, there are numerous websites like Amazon website, Flipkart website, any online portal, so many transactions are being handled. So these are all contributing towards big data. Stock market, of course, like each minute the stocks goes for a particular company, let's say the stock can go up and down. This information needs to be telecasted, needs to be captured. So all these things contribute towards big data. Okay, there are many more, but that I just talking about this 5. Okay, use cases of big data. Let's know. First is recommendation engines. Basically, I think you all might be aware of recommendation system. Let's say Netflix or YouTube. The first time you log into YouTube, they let's say they give some random suggestions to you. Okay, but once you start watching the videos of your taste, then after some time it is able to determine that okay, this guy has interest in this kind of videos. Then your automatically your recommendation changes based on your data that you have provided to them, your search history, your viewing history, I would say. Okay, so they captures your data and gives you better suggestion. Same with Netflix, right? So they utilizes your data which is generated by you. Okay, so recommendation systems is one of the use cases of big data. Even if you go to any Flipkart kind of thing, so once you do some type of shopping, they would suggest that okay, since you bought this, maybe you also like this. Okay, then your CDR, that is called detailed records, which is a particularly telecom based record file which they store with them. Okay, with your every call that you are making has an associated CDR record with it. So with these records, they are able to better suggest you that okay, better identify that okay, this kind of person needs this kind of offer. Maybe you are talking at your night hours too much, though they will come up that's with such decision that okay, here is a special package for you with this much of discount, or let's say this month this much of whatever, your call rates are reduced. Okay, so they will come up for better suggestion for you so that you can spend better more on them and they get the benefit out of it. And fraud detection. Okay, fraud detection is also done with the help of data. Let's say I have a debit card, I swipe it in New Delhi, let's say now I'm swiping it now. Okay, if I was not giving a session, let's say I'm swiping my debit card. So just after half an hour, there is a swipe from the same debit card number in US. Okay, so is it possible for a person to be in from New Delhi to US within half an hour? That's not possible, right? So the systems must look into your data that okay, this seems to be a fraud because half an hour earlier this was swiped from India. Okay, so this kind of any kind of alarm or notification should be raised to the bank immediately. Okay, and that person should also know about it. Okay, so that he can take the necessary steps of like blocking the debit card or whatever needs to be done. Okay, so these are all done with the help of data. Then market basket analysis. Market basket analysis is an interesting kind of analysis where let's say you go to a shopping mall, let's say in the morning for to purchase let's say thing like bread and butter. Okay. Next, so I go in, I take suppose bread and milk. Okay. So we both came out with one person with bread and butter, and I came out with bread and milk. Okay. So let's say there are a few more customers who is having this kind of breakfast. So the common analysis that we can make there, since the person one bought bread and butter and I brought bread and milk, so there has to be relation between within the butter also, and so that now I will keep the butter with the same shelf or the shelf that is nearby milk and bread. So if a person comes in and let's say he picks up bread and butter, then he will also notice into milk. Okay, okay, that's fine. I will buy milk also. Okay, so they play with your they analysis on they do the analysis based on your basket that you are purchasing. Okay, so every mall has a strategy of placing their items. Okay, you go to buy one, your eye fall into other section which is nearby, you pick from that section as well. Okay, so yeah, then next comes sentimental analysis. Sentimental analysis is basically let's say topic which is done by any firm or something which gives up puts up a random topic. Okay, let's say what will be the economy growth of let's say India in next 5 years. Okay, and let's say we as a people, we submit our petition, let's say, or we submit our uh, let's say comments on that. Then based on those forums, they try to analyze the sentiment of a person. Let's say how many person are saying positive thing and how many person are saying actually the negative thing. That can be any sensible topic which they want to identify that how the people of our country is thinking. Okay, so this is kind of sentiment analysis. Okay, here a bit of machine learning is also involved, NLP kind of thing is also involved, but but the base is that we need the data, this big data. Okay, yeah. So yeah, though the challenges that we face in our day-to-day life with big data when dealing with big data is that the capturing of data, since the data is coming from so many various sources, that let's say your data may be coming from a website, your data may be coming from a let's say a mainframe system. Okay, your data frame be coming from any kind of continuously generating system. We call it a streaming system. Okay, your data may be coming from RDBMS. Okay, so data is coming from various different sources. So capturing of data from all these different sources and storing into one storage is one of the challenge. Okay, then curation, since the data is coming from different sources, we need to integrate that data from various sources and put into a storage. Okay, this is one kind of issue challenge, that is integrating the data. Okay, then storage, of course, like there is so much of data that is coming from various sources. Okay, let's say I would say, let's say Walmart. Okay, Walmart has their stores and their website. So data is coming from even from the stores and even from the website. Okay, so you can so much of data and it needs to be stored. So while storing the data, we can't store every data because storing has a price associated with it. That's the we are doing a cloud storage, so it has a price associated with it. Then we need to filter out the data which is not kind of required to us. So this has a challenge that we should be able to figure out that which is very important data to us and which you can discard. Okay, then since the data is of so huge, searching of data, figuring out the right data that we need or that we need is again a challenge. Then let's say sharing of data, let's say the data which is accumulated from one from one business unit needs to be shared with another business unit. Let's say the sales data needs to be transferred to the shared with the finance department. So again, since the data is so huge, again the sharing is an issue. But these things have been taken care by cloud nowadays. Good, but still this is a issue. Okay, transfer data, again, like sharing and transfer is almost kind of similar only. Okay, analysis, again, the thing with analysis is that since our data is so huge, to figure out actually that what is the pattern, or what is the result out of the so humongous data that can conclude is is actually uh, a challenge. And this is why the big data guys or the data scientists are getting paid more, okay, because this is really a tough job. And then again, presentation of the data, which is predominantly done by your data analyst. The data that is generated are presented in the forms of graphs and charts, so that it is easy to so that it is representable to the business users, okay, let's say your customers, okay. Because if you give like a data to them, they won't be able to understand it. If I say, let's say if I give them a form of table in rows and column form, they might not be able to understand it properly. So the data needs to be presented as well, okay. So these are on and on the things that we do in a day-to-day basis, okay. Yeah, so let's look into the traditional approach. How the traditional approach, how was our traditional approach when, let's say, way back in 90s, okay. Actually the size of data at that time was not that much, okay. We didn't have social media that much. We didn't have so much of bank transaction. We didn't have so much of CCTV footages, okay, at that time of point, okay. So data was limited. So we were able to handle those data with, let's say, one DBMS, let's say any choice, let's say Oracle, or let's say Postgres or MySQL, okay. This kind of one database was capable enough to process those data. And there was a application, okay, which is to interact with the user. As you can see in the slide, there's an application which is used to interact with the user, and finally this application is connected with a DBMS, okay, a database. So the system gets the data from the DBMS, processes the data, and serves the user, right? Yeah, so this was our enterprise approach, and it is a traditional enterprise approach. So this has a limitation, right? So the limitation is that, yeah, since the data is earlier it was in small size, as I had said, so it was okay. But when it comes to dealing with humongous set scalable data, then the processing is by a single database is like a bottleneck. It chokes up the system. I am not saying that it will be not able to process, but let's say your processing needs 2 to 3 hours to give a result, and waiting for 2 to 3 hours or 4 hours, let's say, to get a result from your data, we can't have wait for that much of time. Let's say there's a fraud detection, as I have said in the example, and if I give you the result like after 3 to 4 hours that, hey, there is a transaction which we suspect as a fraud, so after 4 hours, what actions you will take, right? So these systems are not capable in that scenarios, okay, since the data size is huge, okay. So how do they work? Let's say there was a very huge the data for, let's say, for a simple example, I'm giving, let's say, 4 terabytes of data, and I have 4 machines, okay. So how we used to do distributed computing in earlier days. Now we are coming a little advanced. Now earlier it was like, here it was like one system. Now let's say we are coming into distributed mode, where you have multiple machines. In my example, let's say I have 4 machines and I have 4 terabytes of data. So I will assign 1 terabyte of data to each of my system, right? To each of my system, I will assign. I will it will be the developer's responsibility to split the data and assign those 4 TB of data into 1 TB each in the 4 systems. Okay. Then I will typically there's a command in Linux grep. Okay, just for understanding, we have to do some coding which will take out our desired record, right? Maybe we don't want entire data to be in our result, so we need to filter the unnecessary records and do some kind of computation on that. Okay, so programming needs to be done, and that programming needs to be done in each individual machine. Okay, then we will get the result. This will produce this result. Let's say node computer 2 is producing the second result, and this all result needs to be aggregated and put into another main result set, which will be a final result set. Okay, so this was our distributed way of doing problem. Okay, So again, this has few issues. Let's see. Now, the splitting of the data to different system was developer's responsibility. What if I'm not splitting the data properly? What if while splitting, I have duplicate records stored in all of the machines? I'll be getting wrong computation output, right? Then coding needs to be done in all the systems. Okay, that means, let's say you are not coding in all the systems. Let's say you're coding in one system, and let's say you're deploying the jar file to every other systems manually. Okay, but that takes an effort. One by one, you need to go to each system, put the jar, deploy the jar, and do the work. Okay, no fault tolerance. Let's say if any of the machine goes down or crashes, I lose my data, right? So there was no fault tolerance guarantee. There is no mechanism to hold the data or store the data as a backup after it is been splitted. Okay, aggregation of data is again the developer's responsibility. Where we should be again writing some code which is capable enough to again aggregate the data from all different sources and integrate into one. Okay, next different challenge was that let's say system A is unaware of the data stored in system B and vice versa, and this may lead to processing of different duplicate data. Okay, because I am not aware what data is being processed in B. Okay, let's say system B crashes, then system A should know okay, system B was processing the data, so now I will process it as well. So this type of mechanism is not there. Okay, so looking into all this solution, Google wrote a white paper in a year, I guess early 2003 or 2004, named as MapReduce. Okay, so they have written a paper in which they have mentioned that there can be a framework named as MapReduce which will do the same task, which will do exactly the same task, but in an automated fashion, I would say. Okay, so the algorithm, this MapReduce algorithm, what it will divide the task into smaller parts and assign them into many computers, as we have seen, but it is in an automated fashion, and collect the results from them, which when integrated form the result set. Okay, the same thing we have seen earlier. Now, okay, now we will look into Hadoop. What is actually Hadoop? Okay, so using the solution which are provided by Google, Kating, there's a person, Kating, who is a kind of the inventor of Hadoop. Okay, and his team developed an open source project called as Hadoop. Okay, this Hadoop internally uses the MapReduce framework. Okay, for processing. Okay, where the data is processed in parallel with other computers. Okay, so there are multiple n number of computers, and they can have their own processing perform in their own machine. So in short, Hadoop is used to develop applications that could perform complete analysis on huge amounts of data. Okay, so there are few components to Hadoop. Let's say for processing, we know that it is using MapReduce. And for storage, it doesn't use the normal file system that we have in our computers or laptop. It uses a special file system altogether that is known as Hadoop distributed file system, which is a kind of distributed application, a distributed storage. Now, your system, multiple systems, is aware that let's say which data is been stored in where. Okay, so this can be tracked. Okay, since it is distributed. Now, and there is one more component known as Yarn, which is a resource management thing. Okay, let's say while launching up an application, while launching up a big data processing application, you need to take care of, let's say, how many nodes and how many compute nodes do I want to process. Okay, and what should be the configuration of each node, and whether this node is available in my cluster, or if not, then how much do I need to wait to get a hold of the cluster or to get an available resource. So these things are managed by Yarn. Okay, I will not go into this one for this session. Okay, so features of Hadoop. So the Hadoop framework is entirely written in Java. Which allows distributed storage and processing of large data sets across clusters of computers. Okay, so I guess by now this statement would be pretty much understood by all of you. Okay, Hadoop follows a master slave architecture. Okay, that means you have one master and you have associated many other nodes to do the processing, which are the slaves. Okay. Hadoop is designed to scale up from a single server to thousands of machines. Okay, so you can scale from one to, let's say, from 5 machines to 10 machines when, let's say, when your size of data increases. Let's say after 2-3 days your size of data again decrease, and you can again scale down your system. Okay, so there's scale in, scale out kind of a technology, supported by Hadoop. Okay, and each node is capable of local storage and local computation. Okay, that means your storage and your computation is done in the same in the same computer machine, I would say. Okay, yeah. Data is initially divided into directories and files. Files are divided in a uniform size block, which is of 128 MB or 64 MB. Okay, so as I was saying, maybe let's go into the example of where we have a diagram. Let's say I have a huge file, this black block, the 4 TB file. Okay, so this block is divided into multiple blocks. Each block is now 128 MB. Okay, so each block now will be stored into different nodes. These are the data node is an slave nodes are known as data node, typically in term context of Hadoop. Okay, so these all blocks will be distributed across my data nodes, of which is of 120 MB. So for a 120, let's say so you can just divide 4 TB by 128 MB and you get that much number of nodes. So these nodes will be stored in this much of how many data nodes you have, that will be distributedly stored in all the data nodes. Okay, and the processing will happen. Okay, the MapReduce will come into picture and take one block at a time and do the processing. Okay, so each data node will have its own HDFS and own MapReduce. Okay, and then the aggregated result will be sent to the name node. Name node is the master node. Okay, yeah. So let's quickly look into MapReduce. MapReduce, as I said, is a parallel programming model for writing distributed application for efficient processing of large amounts of data on clusters, okay, of commodity hardware in a reliable, fault-tolerant manner. And the reason Hadoop gained so much of popularity because we did not need any kind of supercomputers or so much of powerful computers. Even our local commodity hardwares were able to do the processing. We connect n number of commodity hardwares and we do the job. Okay, so this is the reason why Hadoop got so much popularity. Now these things have been taken into cloud. So again in cloud, let's say in Amazon or let's say in Google GCP kind of platform, we again create such kind of minimal nodes, I would say nodes, having let's say 8 GB of data, RAM, and let's say 64 MB of storage, and we let's say I create 5 nodes like that, and I can do the processing easily. Okay, I don't need any kind of supercomputers for that. Okay, so MapReduce programs runs on Hadoop, which is in Apache. Yeah, this is pretty much clear. Okay. Yeah. So how does MapReduce actually work? So MapReduce precisely have 2 phases. One is the map phase and one is the reduce phase. Okay. So MapReduce. Okay. So map phase, what it does, it takes a set of data, converts it into another set. So it takes the set as input and converts that set into another set. Okay. Where individual elements are broken down into tuples, let's say key value pairs. Okay, we will look into an example that what is the key value pairs. But just remember, it takes an input as a data and converts it into another input of data. Next comes the reduce phase, which reduce phase takes the output which is generated by the map phase. Okay, so the output of the map phase is taken by the reduce phase as an input. Okay, and these key value pairs are combined. Okay, as an input and combines those data tuples key value pairs into smaller set of tuples. That means kind of we do the aggregation. Okay, let's look into an example. So this is a typically a word count problem. Let's say we are doing on a humongous file. Okay, so since this is an example, I have, this is restricted to hold a few number of words only. Okay, so dog, cat, rat, car, these are the words that are here. So the first thing is that now we need to split the data, right? Remember, we need to split the data into, let's say, 3 nodes, 3 computers. So splitting is done. Okay, now your HDFS is responsible to split the data. Okay, your HDFS is responsible to split the data. Earlier, the developer was responsible to split the data. Okay, now once the splitting is done, then the map phase kicks in. Map reduce phase kicks in. Your means your data is into the HDFS properly placed. Okay, and now the map reduce kicks in. So what does map phase do? Map phase takes the data from each computer. It will take the respective block of each computer, okay, and convert into key value pair. Remember, key value pair. So it will just append your dog 1, cat 1, rat 1, like this. It will append. Okay, so it's a key value pair. So dog is the key, 1 is the value. Now there is a phase shuffling, okay, which is optional, which may, it depends upon scenario. If any shuffling is there, it will take place. Otherwise, directly it will go to the reduce phase. So shuffling, what is that? Is that it creates blocks where the similar type of data goes into the similar block. So now I get 4 blocks because I have 4 distinct key values. Now my distinct values are 4, so that many number of blocks I get. After that, the reduce phase kicks in, which is just reduce. Now dog 2, car 3, cat 2. Okay. Then the final aggregation is done, which is done by the reduce phase, and it will be reduced here. Okay. So the final result, and this output will be served to the user. Okay. So this is how your MapReduce works in. So yeah, this is the MapReduce approach. As we have seen, big data, split, then map it to key value, then reduce it, and they get all the results. So whatever we have seen in the traditional approach are similarly done in MapReduce approach or the Hadoop approach as well. But now the thing is that it is automated. Splitting of data taken care by HDFS. No more a developer's responsibility. MapReduce, it will automatically kick into every node or every block of data is here. Every block of data it will kick in. Okay. Again, the developer's responsibility is gone. Okay, to put the code, to run the code in all machines. Then again, aggregation of data will be done by the reduce phase. Earlier it was developer's responsibility, and then it will show the result. Okay, I missed one point. Since we have talked about challenges, okay, no fault tolerance. Okay, so how come fault tolerance is there? So let's say I have multiple blocks. What does this arrow represent? Okay, this means that block 1 is also replicated to block data node 2. Data node, this block 2 is also replicated to data node 1. Okay, let's say if any case my data node 2 goes down, then now the data node 1 is responsible to process block 1 as well as block 2, since it is aware that which data is stored in which name node, data node. And this information, let's say which node got crashed or down, this information is stored in the name node. So the name node will immediately trigger to data node that, hey, all the data that is stored in node 2 should be processed by node 1. Okay, because node 2 has gone down for some reason. Okay, yeah, this gives us the fault tolerance power. So this is the big data or the Hadoop ecosystem, I would say. At the first, we have the data ingestion layer, means how the data will first land into your storage layer, HDFS, because your data may be in let's say RDBMS. Okay, your data may be from Twitter. Okay, so this data needs to be first integrated, right? First challenge, integrated, curated, I would say, into one place and stored into one place. Okay, so we have frameworks for that. Let's say SQOOP, which brings data typically in and out, import and export into a RDBMS. Okay, Kafka for any kind of streaming application. Okay, let's say from Twitter, Kafka can bring in. Flume is also a streaming platform, but now kind of it has got deprecated. Okay, now we use Kafka for streaming. Okay, there are a couple of more, like NiFi is also there. There are a couple of more as well. Okay. Now the data has been ingested to your storage layer. And for streaming, we also have actually Kafka works both for streaming and as well as batch, okay, as well as batch data. Batch data is means, let's say, the data which is generating every after few it has a definite frequency. Let's say every 1 hour, let's say every 1 day. Okay, and streaming data is that continuous data which is being generating continuously. So Kafka can bring data from batch as well as streaming. Okay, and to bring up streaming data, which is being generated every second, we have Spark streaming and Storm. Okay, so these all data is bought into a storage. Okay, like that's the HDFS. Okay, now the data formats. What should be the data formats of the file that is being stored in the HDFS? The data which are bought from these platforms no, should be stored in some formats, right? JSON format is there, or CSV format is there. Okay, but typically we use no, for big data processing, for efficient processing, there are some kind of special formats. Parquet format is there, ORC format is there, Avro format is there. Okay, Avro is kind of a row-based format, and Parquet and ORC are kind of column-based formats. So those file will have those format, and it will be stored in HDFS. Okay, so instead of storing a JSON file in HDFS, now we store, let's say, Parquet file in HDFS. Okay, and on the top of HDFS we can have a database. Okay, let's say a NoSQL database, kind of HBase. Okay, which will sit on top of HDFS. Okay, so that you can be able to write queries and get the result out of it. Okay, if you don't want to do map reduce kind of work. Okay, yeah. Then above this we have the resource management. Okay, we have the resource management, and just to say that HBase, to query upon HBase, you need some other framework like Phoenix, which will provide SQL capabilities to HBase. Okay, yeah. If you don't want to write MapReduce code, because MapReduce code is typically written in Java, and there may be programmers, there may be people who are not comfortable with Java and they are comfortable with SQL. So they will use HBase, and over the top they will use Phoenix, okay, to get the result or do the processing. Yeah. So again, in top of them we have the yarn, which is to negotiate the resources. For processing we have MapReduce. Okay, we also have Spark. Okay, which is the most demanding big data technology these days in the market. Okay, for processing we have MapReduce, and now we have Spark. Okay, and for analysis we have Pig, which is kind of deprecated. The Pig is a scripting programming language. Hive works on top of MapReduce. It's a query language developed by Facebook. Okay, this Pig was developed by Yahoo. Okay, um, so Hive, you can write query language over Hive, which will internally trigger the MapReduce job. Okay, then they have Impala. I guess Impala was developed by Cloudera. Okay, yeah. So again, it has SQL capabilities. Just in case everyone is not comfortable with MapReduce, Java is not comfortable with Java. Then we have Spark SQL, which internally kicks the Spark. Okay, not MapReduce. It works on Spark SQL works on Spark. Okay, and Spark MLlib for any kind of machine learning kind of thing. If you want to do machine learning, then we have Spark MLlib. If you want to do any graph computation, then we have GraphX, Graph Frames, which with all these three components works with Spark. They don't use MapReduce. Okay. Then again, for searching big data into big data, we have Solar, we have Elasticsearch. Okay. Then for presentation and visualization, we have Hue, we have Tableau. These are typically used by the business data analyst. Okay. Then let's say for workflow scheduling, let's say we have Uzi. Let's say every hour I need to do the similar kind of job. I bring the data from SQOOP and I put it into HDFS. Then I do the processing using Spark. So this is kind of repetitive work, right? Then I can schedule my job, this flow every hour, and Uzi will take care. Okay. We have one more component known as Zookeeper. Just in case, let's say this is also a kind of resource management coordinator tool. Just in case any of the framework doesn't have their own resource manager. Let's say just like MapReduce has its own resource manager like Yarn. So Kafka doesn't have its own resource manager. Okay, then Kafka will use Zookeeper. Okay, and these are the various managers or the I'd say vendors that provides us these facilities. So Mapr, Hortonworks, and Cloudera, now these are merged into one. Cloudera and Hortonworks recently got merged like 1 year ago or 2 years ago. Now they are only one, Cloudera, and Mapr is there. So these companies or managers provide us the support of this ecosystem. Okay, they are the vendors. Okay, or it means they give us a platform where all things are, let's say, pre-installed or pre-configured. But if you want, you can configure it yourself and not taking help of these vendors. Okay, you can take your own free kind of Ubuntu system and set up all things by yourself, whether in cloud or in your native machine. Okay, so yeah, building career in big data. So I assume my target audience is like BTech and MTech folks. Okay, so I'm not talking for the experience perspective. So to get into big data, you need to be good in few things. That's a programming language, very important. Python, Java, Scala. Okay, these are the three programming languages you should know very well to land into any big data job. Okay, and you should be very good with data structures. Okay, so your programming concept, all in all, should be very good. Okay, then comes SQL. You need a good understanding, good knowledge of SQL. Okay, then you should know about distributed computing. Okay, I know we in BTech we get a subject called as distributed computing, but many people don't take it seriously because it is a theoretical subject. Okay, but you have to understand. You need to have the understanding of distributed computing. Okay, as we have seen, this is all distributed computing. Big data is nothing but distributed computing, right? So like, what is parallel processing? Okay, these things should be clear. Okay, then comes, you should be a bit familiar with cloud. Okay, any cloud like GCP, AWS, Azure. These things are very needed these days, because as the technologies are booming up so fast and people are so advanced with their skills. To compete with the market, you need to have these skills. Okay, then if you know any big data specific technologies, okay, because as a fresher nobody will expect you to know big data technologies, but if you know, it's good. It means, let's say if you have done one or two projects in projects around big data, let's say a college project or a project that you have done from your own interest, which has some kind of technologies from this ecosystem. Okay, let's say which must have Spark. Okay, because that will give you some very good advantages, because it's the most demanding tool. No matter what big data developer across the industry look in, every industry will ask you Spark, and these are kind of optional. Means some companies may want Kafka, some companies may want let's say HBase, some companies might want Hive. These are optional depending upon a very company to company. But Spark with a programming knowledge, that's a Python or Scala, is mandatory for every big data guy. Additionally, Kafka, if you know very well and good, okay, it will add very good value to your resume. Okay, then some kind of a NoSQL database. Okay, you should know, like Cassandra or something. Okay, yeah, that's all from my side. So we will be taking the Q&A according to the availability slot. Yeah, so thank you.
So,
This was all from
there's
my
a
side.
question. There's a
Yeah.
question for you.
Mhm.
How do you build your interest in the early days for big data? Like if someone is just starting out in big data, how can they build up their interest in the field?
Okay, how did I build up my interest? All right. Okay, so back in let's say 2015 around. Okay, so I have to do my MTech. Okay, I plan to do my MTech. Then I figured out that what are the technologies that are more demanding these days, or going to be demanding. Okay, so few other options I found out, like cloud was there. Okay, big data is there, machine learning is there, and then cryptocurrency, I mean Bitcoin was there, blockchain was there. Okay, so now I was unaware that what was big data, what was cloud. Okay, means I didn't have much knowledge, so I started learning, about these technologies one after another in small pieces. Okay, let's say I've started learning cloud last BTech semester days. I've started learning a bit of big data. Okay, uh, then I found out that, okay, since I have good and interest in, since my interest was on programming and DMS, these are kind of my I was strong at my college days, so I found big data to be of my interest. Okay, it was very, so when you keep on studying something, automatically you find out your interest. Maybe some other upcoming engineers might not be familiar with big data, might not have interest in big data. So just looking at the market trend, by getting influenced by someone, that since he have the job in big data, I will also move towards big data. No, don't do that. Study about different flavors. Okay, study about DevOps. What is DevOps? Study about cloud. Study about crypto, blockchain, and try to figure out what is the best, in which thing you got the most interesting for you. Just focus on that. Okay, even somebody asked me over LinkedIn, this new students, the upcoming engineers, or whoever asked me that I want to shift towards big data. I typically ask the question, why big data? What's the reason? I just want to know, is it looking to the someone that he have chosen big data, or he have come up with some concrete results that, oh, this is why I have come with my big data, because this is of my interest. So explore different technologies, find out your interest, then choose this line. Otherwise, you will be frustrated at the end that, hey, I am not good at this technology. I don't know, and I don't want to do distributed computing. Yeah, that's the thing. You will be into problem then.
So there's a question regarding the roadmap. That is it like first you do AI and ML, then you move on to big data, or
no, AI
are they
and
even
ML,
connected?
AI and ML are different tracks altogether. Okay, for big data, as I said, you need to be good in programming, data structures, SQL. Okay, you need to have the knowledge of cloud, distributed computing. There are lots of things into big data. Okay, for machine learning people, you don't need to understand distributed computing. Like, big data guys are the responsible person who will collect all those huge data, process them, and confine them. Right? It will be confined, and then we will give only the confined data to the machine learning engineers, so that they can run their predictions over those, analysis over those confined data. Okay, so they are not responsible for doing distributed processing. Okay, they are just responsible to run their models on the specific data, on the concise data that we as a big data engineers give to them. Okay, so both have different responsibilities. We are actually responsible for managing the data, storing the data, transforming the data. Okay, big data machine learning engineers are responsible to find the analysis on the data. Okay, so they should be good in Python. Their number one programming language is Python. Then they need to be good in SQL. Okay, then they need to be very good in statistics, because machine learning is 70 to 80% of statistics only. Just the thing is that you need to implement those statistics thing in a programming language. So you don't need to focus on these things in which I said in big data. Rather focus in statistics. Rather focus in SQL. Okay. Then comes some frameworks for AIML, like Keras. Then there are few other TensorFlow. Yeah, these things comes into picture. Then you can slowly adapt those frameworks, but don't jump into the frameworks directly. Understand the core first, because whenever you need to solve a problem, you have to think as an engineer from the core. Okay, that actually this is the problem. Now, how can I solve it? People just start learning from directly jump to frameworks instead of understanding the core. Like, if I don't understand that what are blocks, how does it stored, how does it replicated, what will I do just by learning, MapReduce, just by learning Spark? It's no sense, right? If I don't know how does it performs internally, how does it works internally? Yeah.
So this is a question that so if you see try to see the future, is it big data or data science, which I will have a better prospect in the future?
None of the things I would say would die, okay, because we complement each other. There is no data science without data engineers, and there is no data engineers without data science. We both complement each other. If there is some master freaks out of there who can say that there are profiles like that, okay, full stack data engineering or full stack machine who kind of do both of the things. They get the data, they process the data, and then also they do the analysis on data. He needs to be a master freak. Yep. We both complement each other. There is no one going out of the picture as I see the market. Yeah.
So
Only thing
thank
only thing if you are capable of doing the both, um, then let's say one of the people will be in danger. Yeah.
So I guess these are the questions. So thanks a lot for coming, sir, for taking out time
Yeah.
for this. It was a
No problem.
beautiful
It was my
session.
pleasure.
It was
Thank you.
amazing to learn more about big data, and we all know how important it is. But how you
Mhm.
explained it was beautiful. Thank you for
Okay.
giving your time, sir.
Yeah. Okay. Thank you. Thank you, Shashwat and Vinamra. Right?
Yes, sir.
Okay. Okay. Chalo then. Okay. We can drop them.
Yes, sir.
Okay. Thank you. Thank you, everyone. Bye.